Well, hi there. So in this video, we're going to be taking a look at module 56, which is our second module in which we practice costs. In this one, we're going to be looking at long-run average total costs. So let's get started. The first question says the accompanying table shows three possible combinations of factory sizes for a candy factory. And for each choice, they give you the fixed cost and then the AVC, and then tell you the AVC is constant for that particular factory size. So the first problem says for each of these three choices of plant size 1, factory size 2, factory size 3, calculate the average total cost of producing 12, 22, and 30,000 pieces of candy a month. So this is going to require a calculator for these because we're going to end up dividing some numbers, but let's see how these turn out. So for plant size 1, right? Plant size 1. The first thing that we need to kind of observe is that the average variable plus the average fixed is going to equal the average total. And that's what we're going to kind of be going for here, is to find these average costs for these three plant sizes if they're producing 12, 22, and 30,000 pieces. So if they're producing 22,000, then we know that the fixed cost, right? So the average fixed cost, the fixed cost is 8,000 for this first plant. And I'm using that, and I'm just going to divide that. Actually, I should have done the 12,000 first. So let me do the 12,000 first and then the 22,000. I had a brain fart there. We're going to divide this 8,000 by the 12,000, and that will tell us the average fixed cost. Then we're going to use that number to add it to the average variable to find the average total. So let's kind of do this 8,000 divided by 12,000. And I know that's a little bit hard to read, but 8,000 divided by 12,000 is 2/3. You could have also just kind of thought about, well, 8 divided by 12, right? Because they're all just zeros that we can cancel out with some of these. So we know that the average fixed is 0.67, and therefore we can say the average total cost equals 0.67 plus that $1, so that's 1.67. And then if they're producing 22,000 units, then we're going to take our 8,000 fixed cost and divide it by 22,000. So again, 8 divided by 22,000 units now gives us 36 cents of the average fixed. So 36. And so therefore the average total cost equals $1.36. And again, I'm just taking that $1 of average variable and adding it to the average fixed that I'm calculating here. And then the last one, if they are producing, our last option is 30,000 pieces, 30,000, we can say the average fixed cost equals, and so this would be the 8,000 of the fixed cost divided by the 30, not 3, 8 divided by, work. So you just will it into existence. 30 equals, finally, 27 cents. Okay, 27 cents. And so therefore the average total cost equals $1.27. And now we rinse and repeat. Now that we know how to do that, right? So plant 2 and then plant 3. And I know this seems like really labor intensive. It is. This is kind of tedious, but this textbook is kind of trying to put you through your paces of, do you understand how these numbers actually get calculated? So if 30,000, there's probably an easier way that I could have written these out than doing it this way. If you come up with a better way, feel free. So now we have plant 2, 12,000 is their fixed cost, right? 12,000 is the fixed cost. If they're producing 12,000 units, then I know the average fixed cost is just $1. So therefore the average total cost, which is 75 cents, is the variable, plus that $1 means equals $1.75. And then for this next one, average fixed cost is the 12,000, which is the fixed, divided by the 22. So 12 divided by 22 equals 55 cents. 55 cents. Therefore, the average total cost is equal to that 55 cents plus the variable of 75, which is $1.30. And then last but not least, if we have 12,000 of fixed cost, and we're going to divide that by 30,000 units, 12 divided by 30 means 40 cents per unit is the average fixed. And so therefore the average total cost is that 40 cents plus the 75 cents. And so 40 plus 75 is $1.15. And then last but not least, 12K, 22K, 30K, therefore, AFC equals Again, there's probably a faster way to set this problem up. You feel free to do it however you want to, because what we're really trying to do is calculate these values. Now we're just going to take this $24,000 fixed cost and divide it by these total number of product. So 24,000 over 12, we could do that in our head. That's $2. The next one, though, is 24,000 divided by the 22,000, which is a little weird. That's going to be $1.09. And then the last one is going to be this 24,000 divided by 30. 24 divided by 30 equals 0.8, so 80 cents. And so then our ATC, 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 which is what we're going for here, is that 25 cents that's in the table. 25 cents is just given to you as the average variable. If we add it to these numbers, that's how we get that. So $2.25, $1.34, and then 25 cents plus 80 cents is $1.05. So from each of these, you can see that the average costs are going to be lower if basically they're producing larger amounts of units, which shouldn't be a surprise, right? The average is going to be smaller. And basically, as the plant gets bigger, we're actually probably reducing these as well. So there's kind of economies of scale is actually how we would describe that. Suppose the firm historically produced 12,000 candies a month. What factory size should they pick? So what we do then is we say, well, if there's 12,000, we have one factory, it's going to cost us on average $1.67. If there's 12,000 and two factory, $1.75, 12,000 and three factory, $2.25. So if we have part B, we should choose plant 1, right? Because the ATC is the least, $1.67 is smaller than a 75 and $2.25. Now, suppose the factory experiences a sharp increase in demand that leads it to produce 22,000 candies. How will the average cost change if you chose option B? Well, it would drop. If we went from 12,000 to 22,000, the average total cost goes from $1.67 to $1.36. So ATC decreases, we would say, from 167 to 136. It just decreases. Now, part D says, explain what they should use if that's a permanent change. So in other words, if we think we're going to constantly be at 22, should we stick with one factory? Should we switch to two factories? Or should we switch to three factories? Well, if we're looking at minimizing our costs, which we may be in this case, we would want to choose plant 2. Switch to plant 2. 2 factories. And that's because our ATC is $1.30 here. That's lower than the $1.36 if we stuck with plant 1. On the other hand, if we thought that it was a temporary change, we would say stick with plant 1. That's all you got to do. I know that this is a laborious task of calculating these average costs, but it's also good practice. So hopefully you were able to follow all of that. Let's do number 2. Draw a correctly labeled graph showing 3 short-run average total cost curves and corresponding long-run average total cost curve. On your graph, identify the ranges for economies of scale, constant, and diseconomies of scale. So our graph for these is going to be kind of a long quantity and a dollar value here. And we need at least 3 short-run average total cost curves. So we're going to put SRATC 1 and let's say SRATC 2. And I'm going to put one back way over here because I kind of know how this shape is going to look, SRATC 3. Now, we know that there's probably a lot more of them, right? There's a bunch more, and they're going to kind of look like that. And there's a zillion of them. What we're going to do is kind of connect these points and flatten it out in the middle, and then it's going to start to come back up again eventually as well, right? So that's our LRATC, our long run ATC, and it's formed through the minimum points of these short run average total cost curves. We would say that here, this is where the kind of decreasing LRATC, and so this is the economies of scale range, the first range, and then move that just a bit, and we have constant returns to scale, and then where that's where the LRATC is staying kind of flat. And then when the LRATC starts to bend back upwards, that's what we call diseconomies or decreasing returns to scale. So you're not kind of getting as much out of it. All right, let's take a look at these multiple choice problems. Question number 1, in the long run, all right, all the inputs are variable. That is true. Success, A. I always like it when the first one's the right answer. It's just a definition of the long run is where all the inputs are variable. Which of the following is always considered the long run? A month, a year, 5 years, none of the above. None of those actually tells us what the long run is. The definition of the long run is that all the inputs are variable. It doesn't, the time is not actually the matter here. Which of the following statements is generally correct? The LRATC is U-shaped. Yeah, sure, we just drew one. It was kind of U-shaped. The SRATC is U-shaped. Yeah, sure, they're usually U-shaped. Okay, so we've got this one and this one. Firms tend to experience economies of scale at low levels of production and diseconomies at high levels of production. Yeah, I would say that that's true. Like the higher the level of production, right? You're kind of thinking through this problem. The reason why I'm not totally comfortable is I'm thinking like, what does this mean? Low levels of production, and like typically actually as you increase your scaling up your operations, we would say you would get economies of scale and then they're followed by diseconomies of scale. So I'm going to go ahead and say sure, true, E for that one as well. I just had to kind of chew on that for a second, make sure there wasn't any weirdness there. When making decisions, which of the following costs should be ignored? So this is something from this section, and these are called sunk costs. Sunk costs, we didn't really talk about them in the lecture because you should ignore them, but a sunk cost is something you've already spent the money on. It doesn't help us make decisions about what we should do next. So when we should make decisions, we should think about the marginal costs as opposed to the sunk costs, which are the ones we've already spent, the money we've already spent it on something, and we have to kind of ignore that. It can be really hard to ignore sunk costs. In fact, it's called a sunk cost fallacy. I remember what that was. But basically, it's this notion that we should somehow care about them. Well, that money's gone. And that's what a sunk cost would be. It's money that we've already spent, and we have to ignore it when we're thinking about decisions about how we should move forward. Economies of scale will allow which of the following types of cities to lower their average total cost of clearing snow by investing in larger snowplow fleets. So I'm just thinking like, okay, if they're scaling up like they're snow plowing, what's going to lower the average cost of clearing snow by buying bigger fleets? Would be if you want to produce lots and lots of units of a particular product. So the more things that you have to do, the lower that average cost would be. And so we would say that the more snowfall they have, because like that actually would reduce the per unit cost of clearing snow. So more snowfall, E would be the only scenario. Although that is kind of a strange way to phrase that question. All right, hopefully this helped you. I'll see you next time.